So now that we had a chance to talk a little bit about how you can organize a stream using the simple search stream program as an example, let's start talking about ways you can create a stream. And there's a whole bunch of different ways to create streams, and they work with things called factory methods. And these factory methods should be something that you're familiar with. The concept of a factory method is hopefully something you're familiar with from other things you may have done in the CS 251 course or 251, where you learned about software design patterns, like the Gang of Four book. And in the Gang of Four book, they have this concept of a factory method, which creates stuff. So there's a bunch of different ways to obtain or create a stream using different factory methods that are supported in the streams framework. And we'll take a look at a couple of them, and you get a chance to use these different methods in your programs. So first thing you can see here, one way to do it is to take a Java collection. In this case, it's just an array or a varargs list. And you say list.of, and you give it a list of strings, or an array of strings, as it were, and that makes a stream. So that's a very simple approach. And you'll get a chance to use that style of approach. The of method will turn out to be useful for various things. Another way to do it is if you already have a collection, like words defined, which you can see up here. So we made ourselves a words defined list. You can then say words defined.stream. That makes you a, So there's more stuff going on here. So you'd have to think of this as words defined.stream ... as I show here. This does not return a list, but that would be what would happen as we went through the different transformations and ended up collecting the results into a list of search results. So words defined just creates a stream, and that creates a sequential stream. And that's what we'll be doing for the first assignment, assignment 1A. And that's the approach that we use here on our simple search stream program in our case study. Another way of doing things, which is equally trivial to do, is just to take your collection and say .parallelStream. And that goes ahead and will create a stream where the elements can run on different processor cores using the Java common fork join pool, which we've talked about briefly in passing much earlier, but we'll talk about in more detail as we go through this. So that gives us a parallel stream. As to whether a parallel stream is better than a sequential stream depends on various factors, such as the so-called n times q model that we talked about. And if you have any questions about that, please let me know. Now, an interesting factoid is you can turn a stream into a parallel stream anywhere along the way up to the point where you hit a reduction operation, like a terminal operation, such as collect or reduce or so on. And as you can see here, what we do is we can start something out as a sequential stream, and then along the way we can say .parallel, and that will convert the stream into a parallel stream. I'll talk about this in more detail later, but it's very important to recognize that you can put .parallel, and even though you appeared to start out as a sequential stream, wherever you put .parallel, the stream becomes a parallel stream the whole way through. So you can't start out by saying .stream, do some sequential processing, then .parallel, then do some parallel processing. Whether something is parallel or sequential is a property of the entire stream, not just where the word appears. And that's very confusing at first glance. The easiest way to not have to worry about that is just to say .parallel stream, in which case you know it's a parallel stream. But there's other situations where, for various reasons, you need to be able to switch from something that begins as a sequential stream, at least syntactically, and make sure it runs as a parallel stream. And that'll become clear later when we talk about the stream of operator. And I'll show you an example of that in just a minute. So there's another way to create a stream, and that's to take an array and convert that into a stream. So before, we just talked about how you can take a Java collection and turn that into a stream. So you can also have an array and turn that into a stream. And here's a couple ways to do it. One way to do it is to use the .stream method on the arrays class. So there's an arrays class, which is a utility class, and it has a bunch of basically factory methods on it. And in this particular case, you can say arrays.stream, take the array, it turns it into a stream. And then you could take that stream and do stuff with it. You could go ahead and you could print out each element, either printing it out using a lambda expression, which is what I show you here, or perhaps better yet, using it as a method reference, which is what's shown at the bottom of the slide. So in that particular case, in either case, whether it's a lambda expression or a method reference, you take each of the elements in the stream and you print it out using the println method. You can also use a static factor method, and this is the of method I was alluding to earlier. So here, once again, we have an array of strings, and we use the stream.of method. And by default, stream.of, or not by default, by design, stream.of returns a sequential stream. So you'll get a stream that's a sequential stream. In this particular case, we take that stream and then we print it out either using for each with a lambda expression or for each with a method reference. Doesn't matter. The key point is it's sequential. So if you don't want it to be sequential, what you would do is you would say stream.of, and then you could say .parallel, which would then go ahead and run everything in parallel. Now, that may be overkill for this example, but I'm just illustrating the point that if you have something that begins as a sequential stream because you used of on it, then you can go ahead and use the .parallel in order to convert it to a parallel stream. There are yet other ways to create streams using static factor methods, and this is a really cool example. This is using the iterate method. And iterate is a method that creates essentially an iterator-like entity. It's not a Java iterator in the Java iterator interface sense, but it plays the role of an iterator. And this particular example is going to generate and print the first 100 Fibonacci numbers, and this is really cool. It's a great example of the power you can do with streams in order to do very sophisticated computations. So we're going to start out by giving it what's called the seed, which is the initial element into the stream. We say new big integer, open close. That says make me an array of big integers. And in this case, we're going to make a 2-element array of big integers, both initialized to the value 1. There's a constant defined in the big integer class called 1. And as you might imagine, it has the big integer value of 1. So we make 2 big integers that are 1. And then we have this next part of the iterate method, which is a lambda function that will be applied indefinitely to the previous element in the stream. And so what we do in this case is we are going to go ahead and take in f, and we're going to say, make me a new big integer, and f stands for Fibonacci, by the way. We're going to say, make me a new big integer, which has 2 elements, where the first element in this big integer array is the Fibonacci value that's in location 1. Remember, arrays in Java start at 0, so this is the second element. So we're going to have the second element as the first element in this new big integer array. And then we're going to take f1 and we're going to add it to f sub 0. So f sub 1 is added to f sub 0. And if you think about it, that's the Fibonacci sequence, right? You take the successive value and you add it to the new value, and then you make that the value in the sequence. So this will go ahead and generate an infinite stream of Fibonacci's forever. But of course, we don't necessarily want to go forever. We just want to stop after a certain value. So we're going to stop after the first 100 of these things. And so check out how we do this. This is super cool. Remember, we've got ourselves a 2-element array which has the Fibonacci sequence in succession, each pairwise element. And we're going to come through and we're just going to take that 2-element array and we're going to map it so it becomes a 1-element array, which is just f sub 0. So that'll be like 1, and then we'll end up with 2, and then we'll end up with, so you just keep adding the Fibonacci sequence stuff together and it just grows and grows and grows. So that's going to make it basically a stream of big integers. And then we use the limit short circuit operation. So the limit short circuit operation is an operation that will stop after the value indicated here in the parameter 100 is met. So when that value is met, then at that point it will go ahead and terminate the stream, and we'll end up taking the first 100 elements in the Fibonacci sequence, and we'll go ahead and print them out using println. Yes?
I just got a little lost in the part where you said it would go in for 50, because I just see you adding the first and the second element, and then how does it go into that?
Great question. So the question was, how does this go on forever? Because this particular iterator lambda expression will be reapplied successively on the value. So every time, each time you apply this particular lambda function, it will generate a new value, which will then be reapplied with that function again, and be reapplied to that function again, and be reapplied to that function again. So this particular sequence will keep going and going, where each time we're going to create a new big integer that will have contained the two successive values for the Fibonacci sequence, and it'll just continue on and on and on. So you can think of this as basically like an implicit loop that just continues. I mean, it actually loops like, while true, and it just does that operation indefinitely. So that will generate an infinite sequence of pairwise Fibonacci numbers that are ever increasing as it goes through there. We then winnow them down so there's just one value as opposed to a pair of values by using this clever map operation, which transforms the type, and then we limit it to the first 100. Yes?
How does limit act in parallel?
Great question. So remember I said before how the operations actually go from top to bottom, left to right. So in a sequential program, it's easy. It just keeps pulling things down until the number of elements that have been processed equals the parameter passed in to limit. In parallel processing, it's more complicated because they have to keep track across all the different threads that are going on to make sure they stop after the first 100 elements. So it's just an internal implementation detail how they do that. However, maybe to the point of your question, it's not particularly efficient. So using limit in a parallel stream works, but it's not the most efficient way to do things. So you probably want to minimize the use of limit with parallel streams, or just not expect to get the boost from parallelism you might otherwise want. And we'll talk about that later. Remember we talked before about how parallel processing works best when you have so-called embarrassingly parallel operations, which means that there are no dependencies on anything. It's kind of like doing your wash. So in this case, if you use limit, you now have an implicit dependency, which is all the threads have to coordinate to keep track of when that limit is reached. So all of a sudden, you don't have just embarrassingly parallel. There's implicit coordination and synchronization taking place. So not surprisingly, that will slow things down. That would be kind of like saying, I'm going to do my wash, but I'm going to stop all the washers after they've cycled 1,000 times, So you'd have to sit there and watch them all going, and it would drive you crazy. So limit works. It semantically is designed to work properly with parallel streams, but it's not as optimized as you might want. So that's a good question. And in fact, so here we're going to print out the first 100 Fibonacci sequences. And in fact, avoid using iterate in a parallel stream in general, especially when you start using it with limit. So it just doesn't work very well in parallel streams. But it works great for sequential stuff like we were showing here. So those are some of the common Java streams factor methods. There are other factor methods in Java streams that create streams, and we'll talk about some of them later when we get to further, more advanced parts of the course. But for right now, this is by far enough to get you started. And the key thing here are the .stream and .parallelStream factor methods. Those are by far the most common ones.